Failure is the vanguard of success. The avenues of endeavor herald discovery. But this path has no end. Space is infinite. The questions are limitless. In a million years hence, we will still look up and ponder what is above and beyond.
Coming right up, the OAO, or Orbiting Astronomical Observatory, has 11 telescopes that viewed the stars with a clarity never possible before 1968. In this edition of Above and Beyond, we revisit the road to success. There were many achievements and some catastrophes that occurred in the lead-up to manned missions to the moon and back. And exercise is the key to good health. However, in space, one element that is necessary to maintain a healthy body is missing: gravity. We have a special report on the effects of long-term exposure to microgravity and how to cope with it. In 1968, the F-111 is able to provide NASA with details of the variable sweep-wing characteristics of supersonic transport. At study speeds in excess of 3,500 miles per hour, the hypersonic X-15 rocket aeroplane is used. The usual jet black X-15 takes on a new appearance as it's painted with a special ablative coating to withstand the searing heat beyond Mach 7. On October the 3rd, Major William Knight sets a new speed record with the newly painted rocket plane, 4,534 miles per hour. As usual, the X-15 is carried aloft by the giant B-52. When the desired altitude is reached, X-15 drops away and maneuvers on its own. Major Michael J. Adams dies in a crash while testing the X-15. The tragedy is the first since the program began in 1959. A so-called HL-10 lifting body is successfully tested this year. Lifting body craft are being studied as a possible means of flying future spacecraft back to Earth after a mission, rather than parachuting into the ocean. A stubby design will allow an astronaut to maneuver his spacecraft back through the Earth's atmosphere and then land like a conventional aeroplane. In 1968, jet aircraft noise is a worldwide problem. While studies are going on to improve existing engines, efforts are underway to produce a completely new engine designed to be quiet. Also, a specially instrumented jet is being operated in a way to decrease the ground exposure to noise. This involves flying the plane in at a steep approach and letting the distance reduce the noise on the ground. Eventually, all the known noise reduction techniques will be combined in an effort to produce a truly quiet engine. By 1968, the moon, not nearly as mysterious as it used to be, has been photographed, landed on, dug into, and chemically sampled. Surveyor 7 is the last in a series of unmanned spacecraft to land there. 5 out of the 7 surveyors launched landed successfully on the moon and operated on the surface. The surveyor photographs show that to land a man on the surface of the moon without sinking into any great depth is a reasonable undertaking. Photos show there to be fewer large rocks in certain areas, but the numerous small craters would have to be contended with. The actual surface material is found to be very similar to a basalt found here on Earth. NASA's Jet Propulsion Laboratory is also applying its scientific know-how to Mars, flying by initially, landing and testing in the future. The experimental model of a wheel-shaped planetary landing craft is one of several landers being considered. In an effort to learn more about the possibility of life on Mars, the lab again sends a team to the Antarctic. Carefully collected soil samples are subjected to rigorous analysis. The Sun, seething and turbulent, affecting everything on Earth. By studying it, we can learn more about our own environment. Interplanetary Pioneer spacecraft are doing just that. Two were launched in 1968. At one point in their voyage, millions of miles into space, they pass directly behind the Sun. The data returned is being used to improve weather forecasting and adding a measure of protection to moon-bound astronauts by forecasting solar activities. Also helping us learn more about the Earth's environment is the Orbiting Geophysical Observatory, OGO-5. By studying such things as our magnetic field and radiation belt, solar flares and solar wind, we gain new insight into the complex Sun-Earth relationship. Radio Astronomy Explorer, one of 5 Explorer-type spacecraft, is launched. While ground-based radio telescopes observe the short radio wavelength, the RIS will make its measurements beyond the edge of the radio window. The heaviest and most sophisticated satellite to be launched in 1968 is the Orbiting Astronomical Observatory. It has 11 telescopes that view the stars with a clarity never possible before 1968, mapping the skies and providing a better understanding of the origin of the solar system and universe. Shortly after launch, Nimbus B, an experimental weather satellite, plunges into the Pacific, just off the coast of California, when a gyroscope malfunctions. Divers recover 2 valuable nuclear-powered generators about 300 feet down. In 1968, the wingless HL-10 lifting body makes 13 flights, including 2 with sustained rocket propulsion. The Flatiron-shaped craft gets its aerodynamic lift from the wingless body shape. Lifting bodies show promise as returnable spacecraft of the future. After 9 years and nearly 200 flights to the edge of space, the X-15 program is brought to close with 8 final flights in 1968. The half-rocket, half-plane has been a unique testbed for researching aeronautics and space problems. The giant XB-70, flying at 3 times the speed of sound, makes 13 research flights, gathering data for use in the development of large, supersonic aircraft. Extensive flight studies are also made on several types of vertical takeoff and landing planes. VTOL, as they are called, can take off vertically, then move forward like any other plane. Much aeronautic research is done with models. In this particular test, a highly instrumented model is dropped by a helicopter, then flown by radio control from the ground. This type of study makes the most rigorous test possible without the danger to a pilot or the expense of a real craft. As already mentioned, jet aircraft noise is a continuing major problem. NASA tries out various engine modifications to find out the effect on an aircraft's performance. It's discovered that by cutting grooves in an airport runway, planes can land with less chance of skidding and stop easier. In 1968, the tests continued. Some of the braking tests are made by using specially instrumented cars on the runways. Now the results appear to have applications to highways as well as landing strips. At the Nuclear Rocket Development Station in Nevada, a powerful nuclear rocket reactor is tested. The tests are part of an effort to develop nuclear-powered rockets for future deep space exploration. Apollo can be likened to a finely tuned watch. Men and space machines are perfected to the highest degree possible. In most cases, the astronauts who fly the spacecraft train separately but concurrent with the build-up and development of the space machines themselves. When brought together, they must mesh smoothly. There is little room for error. Apollo is like this, and the men who fly and the men who build know it. There are 4 Apollo flights in 1968, 2 unmanned and 2 manned, all part of the preparation for moon landing. Apollo 5 sent aloft to check out the lunar module. It's in a lunar module that 2 astronauts will land and take off from the moon. Both the descent engine used to slow the spacecraft for the landing and the ascent engine that will boost the pair off the moon are successfully tested. To further ready the Saturn V rocket and its many components, the unmanned Apollo 6 is launched into orbit. Engineering cameras on board record the first stage and interstage separation. After 10 hours in space, the command module is rammed back into the Earth's atmosphere, simulating a lunar return. Another milestone in preparing for moon mission. The next step, check out the spacecraft with men aboard. Here, astronauts Schirra, Cunningham and Isley move about weightlessly in their Apollo 7 spacecraft. This is also the first full dress rehearsal for the manned spacecraft tracking network. 14 ground stations located in such places as Bermuda, Australia, Spain and Hawaii, together with planes and tracking ships, keep an electronic ear tuned to the Apollo spacecraft. After 10 days and 163 revolutions, Apollo 7 splashed down in the Pacific, paving the way for the first half-million-mile journey to the moon and back. The Saturn V rocket boosts the Apollo 8 astronauts, Borman, Lovell and Anders, toward their rendezvous with the moon. The first time the big rocket is flown with men as passengers. While en route, the crew keeps busy checking and double-checking all systems as they speed towards the moon. Many of the things they do are to have direct bearing on the future lunar mission. Nearly 3 days and 230,000 miles later, the crew of Apollo 8 fire their rocket engine, placing them in lunar orbit. Here are some of the views recorded by the crew as they orbit 10 times, showing remarkable detail. The kind of detail needed before man can land there. Then the cameras and spacecraft are turned towards Earth. And after 3 days and a fiery re-entry, they land in the Pacific within sight of the recovery ship. Apollo 8, final flight of the year. Historic prelude to the lunar landing and to the peaceful exploration of space in the future. Gravity hurts. You can feel it hoisting a loaded backpack or pushing a bike up a hill. But lack of gravity hurts too. When astronauts return from long-term stints in space, they sometimes need to be carried away in stretchers. Gravity is not just a force, it's also a signal that tells the body how to act. For one thing, it tells muscles and bones how strong they must be. In zero-G, muscles atrophy quickly because the body perceives it doesn't need them. The muscles used to fight gravity, like those in the calves and spine which maintain posture, can lose around 20% of their mass if you don't use them. Muscle mass can vanish at a rate as high as 5% a week. For bones, the loss can be even more extreme. Bones in space atrophy at the rate of about 1% a month, and models suggest that the total loss could reach 40 to 60%. Blood feels gravity too. On Earth, blood pools in the feet. When people stand, the blood pressure in their feet can be high, about 200 millimeters of mercury. In the brain, though, it's only 60 to 80 millimeters of mercury. In space, where the familiar pull of gravity is missing, the head-to-toe gradient vanishes. Blood pressure equalizes and becomes about 100 millimeters of mercury throughout the body. That's why astronauts can look odd. Their faces filled up with fluid puff up and their legs, which can lose about 1 liter of fluid each, thin out. But that shift in blood pressure also sends a signal. Our bodies expect a blood pressure gradient. High blood pressure in the head raises an alarm. The body has too much blood. Within 2 to 3 days of weightlessness, astronauts can lose as much as 22% of their blood volume as a result of that errant message. This change affects the heart too. If you have less blood, explains Dr. Victor Schneider, Research Medical Officer for NASA headquarters, then your heart doesn't need to pump as hard. It's going to atrophy. The question is, do such losses matter? Well, perhaps not if you plan to stay in space forever, but eventually astronauts return to Earth, and the human body has to readjust to the relentless pull of gravity. Most space adaptations appear to be reversible, but the rebuilding process is not necessarily an easy one. Each of the parameters have their own normal recovery time. Blood volume, for example, is typically restored within a few days. Astronauts get thirsty when they come back because their body says you don't have enough blood in your blood vessels, and that causes the messengers to say, drink more. Also, the body doesn't urinate as much. Muscle too can be recouped. Most comes back within a month or so, although it might take longer to recover completely. We normally say that it takes a day of recovery on Earth for each day that somebody's in space. Bone recovery, though, has proven problematic. For a 3 to 6 month space flight, it might require 2 to 3 years to regain lost bone if it's going to come back, and some studies have suggested that it doesn't. You really have to exercise a lot. According to Dr. Alan Hargens, recently of NASA Ames and now a professor of orthopedics at the University of California, San Diego Medical School, it's important to keep astronauts in good physical condition. You want the crew members to function normally when they come back to Earth, and not have to lie around for long periods of rehabilitation. And Earth isn't the only planet that astronauts might visit. One day humans will journey to Mars, a 6-month trip in 0G before they disembark on a planet with 38% of Earth's gravity. We'll have to maintain those astronauts at a fairly high level of fitness. When they get to Mars, there won't be anyone to help them if they get into trouble. They'll need to be able to handle everything themselves. Exercise is the key, but exercising in space differs from exercising on Earth. Here, gravity's pull automatically provides a resistive force that maintains muscles and bones. In space, even if you do the same amount of work that you were doing down here on Earth, you've missed that gravity component. Various devices have been developed to mimic the help that gravity provides. One Russian experiment provides resistance by strapping jogging cosmonauts to a treadmill with bungee cords, but that particular combination has not yet proven effective in preventing bone loss, perhaps because it can't provide sufficient loads. Straps are so uncomfortable that the cosmonauts can only exercise at 60 to 70% of their body weight. There's also IRED, a NASA-developed interim resistive exercise device. iRed consists of canisters that can provide more than 300 pounds of resistance for a variety of exercises. Its effectiveness is still being monitored. Yet another promising device attempts to mimic gravity even more closely. Hagens and his colleagues are developing a lower body negative pressure device, a chamber that contains a treadmill that relies on the suction of an ordinary vacuum cleaner. Hagens says that they found they can provide body weight by applying negative pressure over the body. The device prevents much of the loss of cardiovascular function and of muscle. It also seems to be effective in reducing some indices of bone loss. One reason is that it allows astronauts to exercise with an effective body weight between 100 and 120% of what they would feel on Earth. Another is that, unlike any previous exercise device, it restores the blood pressure gradient, increasing blood pressure to the legs. There's growing evidence that the body's systems interact with each other. For example, you can't just put high loads on the bone and then expect it to recover if you're not taking care of the blood flow to that bone as well. Scientists aren't yet sure how gravity signals the body to keep bones and muscles strong. We know that somehow gravity is converted from a mechanical signal to a chemical signal, and we know a lot about these chemical signals. The mechanical signals, though, remain a mystery. Solving these problems could lead to better therapies for people who aren't using gravity properly here on Earth. Aging is the perfect example. Zero-G living mimics closely the effects of old age. Like astronauts, the elderly fight gravity less. They're more sedentary, which triggers the loop of muscle atrophy, bone atrophy, and lower blood volume. If researchers can identify the signals that generate strong muscles and bones, it might be possible to get new pills and do exercises that would trigger those signals here on Earth. We've just begun to do research looking at the changes that can happen to humans. There are so many wonderful questions, and the answers, they're waiting for us up there in space, where the absence of weight reminds us that gravitation isn't all bad. Sometimes it's a struggle, our daily contest with gravity, but now we know the struggle is good.